ਹੈਲੋ ਮਾਈ ਡੀਅਰ ਸਟੂਡੈਂਟਸ। ਅੱਜ ਦੇ ਇਸ ਲੈਕਚਰ ਦੇ ਵਿੱਚ ਅਸੀਂ ਗੱਲ ਕਰਾਂਗੇ ਅਬਾਊਟ ਦੀ ਕਲਾਸੀਕਲ ਆਈਡੀਅਲ ਗੈਸ theory in canonical ensemble, and in this lecture we will derive the expression for classical ideal gas, and we will find out the partition function, and from that we will find out the various thermodynamic parameters. So before starting this classical ideal gas expression for this canonical ensemble, so I would like to express some alternative approach which we can use in order to find if the energy levels are degenerate. Now in most of the physical cases, the energy levels which are accessible to a system, they are degenerate energy levels. So each energy level, it has a group of states. So it can be, you can say, like GR and group of states, or we can say GR states, they belong to same energy. So similarly, so this GR state, it changes with respect to time as the value of this energy, so it is being changed. So for this appropriate formula for the partition function which we have used in our previous lecture, so that is equal to summation of exponential of minus of BER, and the modified formula for the degenerate energy states, so that we will write it as the summation of R, which varies from 1 to infinity, and that is equal to GR exponential of minus B into R. So in this the energy level ER, it has some finite value for this GR energy states, and the probability density which we have written exponential of minus BER over summation of exponential of minus BER, and the modified expressions of this probability for this degenerate energy states, it becomes GR into exponential of minus BER over summation of GR exponential of minus BER. So we have added this extra energy term, that is the energy states. How much it means that how many systems they are at present which is having the same energy value at a particular instant of time. So thus the probability for this system to be in any of the states with energy ER, so this probability from this expression, we can say it is directly proportional to this energy states, or you can say that is the multiplicity level. So this GR represents the multiplicity level of energy. So this GR, it plays the same role as the statistical weight factor which we generally study in our nuclear physics or all the other quantum problems. So the actual probability is thus determined by both this statistical weight factor or this multiplicity level and this Boltzmann factor. So this probability, now it is dependent upon GR, and it is also dependent upon this exponential of minus B into ER. So if N and V, they are very large, and the energy value, so they ER, so for a very large system, so this energy value which are discrete, so they are very close to each other, and the total energy of this ensemble, it is considered as a continuous energy. So it is something like, suppose if there are very large system of the order of like 10 raised to power 23 system in an ensemble, and each system they are very close. And when you study if for such a large problem and it consists of that the total energy, it is looking like a continuous energy distribution. So therefore, for continuous energy distribution, we generally represent this probability as PE into DE. So it means that the given system, it has a specified energy range, and we can generally write it as it is directly proportional to exponential of minus BE, and our statistical weight factor, that becomes GE. So GE here, that is representing the density of states around energy E. So our modified expression for this continuous energy distribution, or for a very large distribution, so this comes out to be exponential of minus BE GE into DE over now this partition function. So we generally write it with the summation. So this is summation, it turns into the integration. So exponential of minus BE GE into DE. So this denominator for a very large distribution, so this is the generally modified expression of this partition function. So the new value with which we can write out the partition function, that is integration of a system from 0 to infinity exponential of minus BE into GE into DE. So this is for this continuous energy distribution. So that is for the classical case, and for the discrete energy distribution. So where the energy value, it is specifically defined or distinguished for each states. So for discrete energy distribution, we generally write out this partition function as GR exponential of minus B into ER. So this is the two expression, or the two way we can generally explain this partition function, and from that we can find out the various thermodynamic parameters of the specified ensemble. So the expression for the expectation value of any physical quantity which we want to calculate, so the physical quantity, suppose it is F. So for this we can write out the ensemble average for this. So it is a function which is function of energy GR exponential of minus beta into ER over the partition function, or we can rewrite this expectation value of this physical quantity F. So that is something like Fe exponential of minus Be GE into DE over integration of this Be GE into DE. So this is for the continuous energy distribution, and this is for the discrete energy distribution. So let us start our classical ideal gas problem for this canonical ensemble theory. So let us say we have a function of any physical parameter, so that we can generally represent it f of q and p, which is dependent upon this position and momentum coordinate. Rho is generally dependent upon this density of states. So d omega, so that is for a confined volume. So P, this rho Q P is a measure of probability of finding these representative point, and this probability it turns dependent upon this correspondence value of energy. So that is for this Hamiltonian function H, which is dependent upon this P and Q. So this density function, so we can generally write it as it is directly proportional to exponential of minus beta into H, P and Q. So for this canonical ensemble, we can write out this physical function f as f, which is integration of f from 0 to infinity exponential of minus beta into h into d omega over exponential of minus beta into h, which is dependent upon this pq. So the denominator of this expression, it is directly related to this partition function of this system. Now we must know the relation between this volume element in the phase space and the corresponding number of quantum states which are present for this system. So number of available microstates, so that is generally represented as the volume of allowed region over omega naught. So that is the volume of one microstate, or we generally write it as h cube if we are talking about the one dimensional 1D particle motion along this three dimensions having 3 degrees of freedom. So number of distinct states, so this volume of allowed region, it is generally represented with d omega. So this is for one particle having 3 degrees of freedom. And if we talk about the number of distinct state for n particle, then our expression it becomes d omega over h raised to power 3n. So for n particles. Now if particles are indistinguishable, so if we cannot distinguish the particles, then this that is the quantum mechanics states, then the number of this distinct states, that is the quantum states, so that we can represent as d omega over h raised to power 3n into 1 over n factorial. So for the indistinguishable number of particles or the number of quantum systems in a canonical ensemble, then the appropriate expression for this partition function, so that becomes, so partition function for indistinguishable quantum state, so that we generally written as Qn, which is 1 over n factorial h raised to power 3n integration of exponential of minus beta into h, which is dependent upon q and p into d omega. So let us try to find out the value of this h, and from that once we find out, we can write this partition function in more precise way. Now you can see that there are no intermolecular interactions So for this, if we assume that there are no intermolecular interactions between the system, then the energy of system, it is entirely kinetic. So our total energy, so total energy function or this Hamiltonian function, so it is purely based on the kinetic energy, and we can write it as E, which is equal to P square over 2m. So we can write out the value of this partition function by putting the value of H. So this is having the potential energy which we have assumed that is equal to 0. So if there are no intermolecular interactions between the energy of systems, no intermolecular interactions. So this partition function becomes, that is 1 over gamma function h raised to power 3n integration of exponential of minus beta summation of I1 to n pi square over 2m into d omega. So this d omega here we can say that is the total volume of this confined region. It is dependent upon this position phase space and dependent upon this momentum phase space. So this we can write out as summation of I1 to n dq into qi multiply by d cube into pi. So that is for the ith state, so which is vary from 1 to n. So this value of partition function we can write it as 1 over gamma function of n h raised to power 3n integration of 0 to infinity exponential of minus beta summation of pi square over 2m into summation of dq qy into d cube pi. So this exponential of this summation, so this term we can write it something like this. So exponential of minus beta into summation of pi square over 2m, so that we can write it minus beta pi square over 2m minus beta p2 square over 2m, so and so. So that is for minus beta pn square over 2m, that is for the nth system. So this we can write out as summation of I1 to n exponential of minus beta pi square over 2m. So putting the value of this exponential function in the partition function, so this becomes 1 over n factorial 1 over h cube at 3n. So integration of d cube q into n summation of exponential of minus beta pi square over 2m into d cube into pi. So here we have done the separation of this position coordinate, and we have written separately the momentum coordinates. So this integration or the summation of this d cube q, so that is equal to the volume of this phase space. So this we can write out as 1 over h cube n. So this is equal to v raised to power n and integration of exponential of minus b p square over 2m into d cube p raised to power n. So if we open this summation, that is for the n systems, so this whole becomes the power of n. So this we can write out as 1 over n factorial over h raised to power 3n v raised to power n, so into 4 pi 0 to infinity exponential of, so this d cube, integration of d cube p, so that is equal to 4 pi p square into dp. So this 4 pi, so that is constant, it comes outside the integration, and the terms which remain within this integration, that is equal to p square into dp raised to power n. Now we will use the standard integration results, so that is integration of exponential of minus ax square into x raised to power n into dx, so that is equal to gamma function of n plus 1 over 2 over 2 into a n plus 1 over 2, the power n plus 1 over 2. So if you check, so this is our have the same integration. So if I write out here this integration term, so the term which is within the bracket, so this term, so this is the same integration. So let us solve this integration first. So 0 to infinity exponential of minus beta p square over 2m into p square into dp. So this is the same as this integration. Here if you compare these two integration value, so a is beta over 2m and n is equal to 2. So when you put these values, so this integration, it comes out to be gamma of n is 2, so 2 plus 1 over 2 over 2 into a, so a is beta over 2m, so we will put here beta over 2m, the power 3 by 2. Now gamma of n factorial, that is n minus gamma of n, that is n minus 1 factorial. So this equation, so this we can write out as gamma of 3 by 2, so that is equal to 1 by 2 into gamma of 1 by 2 over 2, beta is 1 over kt. So this equation becomes 1 over 2m kt power 3 by 2. So this becomes under root, so this 3 by 2 under root of pi. So this gamma of pi, no, sorry. So this gamma of 1 by 2, so gamma of 1 by 2, that is equal to under root of pi. So this becomes under root of pi by 4. So this terms go when upward, so this we can write it as 2m kt the power 3 by 2. So putting this value of this integration, so our partition function, it becomes 1 over n factorial over h raised to power 3n into v raised to power n, and the term which is within the bracket, that is 4 pi into under root pi over 4 2m kt power 3 by 2 the power n. So this 4 and 4 get cancelled. So this pi, so when goes within this square root, so this becomes pi 3 by 2. So we can rewrite this value of partition function, that is v raised to power n over n factorial h raised to power 3n pi 3 by 2 into 2m kt the power 3 by 2 raised to power n. So this is 3 by 2 power, this is 3 by 2 power, so we can write it as qn vt, so that is v raised to power n over n factorial h raised to power 3n 2 pi mkt power 3 by 2 and whole power is n. So if we move these v raised to power n and h raised to power 3n within this Bractor term, because n power is common here, nth power is common here, and nth power is common here, so we can write this partition function as 1 over n factorial v into 2 pi mkt over h square power 3 by 2 whole power n. So this is the value of partition function for the classical ideal gas in canonical ensemble. Now once we find out the value of this partition function, from that we can find out the various thermodynamic parameters such as Helmholtz energy, Gibbs free energy, value of specific heat, pressure, temperature, chemical potential, and so and so. So from that we can find out the Helmholtz free energy. So this we have studied in this previous lecture. It is equal to minus of kt log of partition function. So putting the value of this partition function q and t within this expression, so from that we can find out the value of this Helmholtz free energy. So this becomes minus of kt log of 1 over n factorial v into 2 pi mkt over h square power 3 by 2 power n. So when we open this logarithmic term, so this we can write it as log of 1 over n factorial plus log of v into 2 pi mkt over h square 3 by 2 power of n. So let us open this. So this 1 over n factorial, that is minus of log n factorial plus this log power, it comes in the front, so this becomes n of log v 2 pi mkt over h square power 3 by 2. So this we can rewrite as minus kt. So this log of n factorial, using Stirling's formula, we can write it as n log n minus of n. So this equation becomes, so let us rewrite this positive term first, n log of v 2 pi mkt over h square power 3 by 2 minus of n log of n minus n minus, this becomes plus. So this is also the logarithmic term, this is also the logarithmic term, so n is common. So taking n common from this, so we can write this term as nkt log of n minus 1, and this minus we have taken also common, so this negative terms become plus, and here comes the negative sign. So log of v 2 pi mkt over h square power 3 by 2. So this we can write as A, that is equal to nkt. So this negative term, it goes in the denominator, so we can write it as log n over v. So 2 pi mkt, it goes in the denominator, h square comes in the numerator, so the power 3 by 2 minus of 1. So this is the value of the Helmholtz free energy. So from that you can also find out the pressure. So pressure, that is equal to minus curly A by curly T at constant n and T. So putting the value of this Helmholtz free energy and taking the derivative with respect to T, with respect to V. So pressure is minus curly A by curly V. So this equation, this comes out to be minus curly over curly V, and writing this value of A, so that is nkt log of n over V h square over 2 pi mkt power 3 by 2 minus of 1, so that is minus nkt. So taking the derivative with respect to V, so this becomes minus nkt for the first term is comes outside. So this curly by curly of V log of n over V h square over 2 pi mkt power 3 by 2 plus curly by curly of V. So there is not any term which is dependent upon V. So this term is equal to 0. So our this equation becomes minus of nkt, so curly over curly V. So open this logarithmic term, so taking the log of n over V plus this powers, it comes at front, and taking the log of derivative of log of h square over 2 pi mkt. So this again this term, so it is not having any value which is related with V, so the derivative with respect to V gives 0, and this equation becomes minus nkt and log of n over V, so this becomes 1 over n over V into minus n over V square. And when you solve this, so the value of P, it comes out to be nkt over V. So that is our standard classical ideal gas equation, which is PV is equal to nkt. So this proves that the value of this partition function and the Helmholtz free energy which we have derived for this classical ideal gas, that is correct. So similarly you can find out the value of this chemical potential mu, so that is curly A over curly N at constant volume and temperature. So so I will not do all those calculations, so you can do at yourself. So if you find it difficult or stuck somewhere, then I can help you. So n over V h square 2 pi mkt power 3 by 2. So similarly you can also find out the value of entropy, which is minus curly A over curly T at constant n and V, and this comes out to be nk log of V over N 2 pi mkt over h square power 3 by 2 plus 5 by 2. So this is the same standard equations which we have derived from this Sackler tetrahedral relation, which we have derived in unit number 1 for the classical ideal gas, and you can relate those values of modified expression of entropy, so which we have find out from this Gibbs paradox. So similarly you can find out the internal energy, that is minus curly by curly of beta log of q and vt. So it comes out to be minus t square curly by curly of t a over t. So you can write it any way. So it comes out to be a plus ts. So this we can write out as 3 by 2 nkt. So that is the internal energy per system for this 3 degrees of freedom. So for the 3 degrees of freedom, or for n particles in 3 dimensions. So this is all about for today's lecture, and in our next lecture we will done some calculations related with this energy fluctuations in this canonical ensemble, and then we will do some examples of paramagnetic problems and the harmonic oscillator problem for this canonical ensembles. So if you have any doubt, you can ask me in the comment box, or you can ask on my WhatsApp number. So I will share all those notes on the WhatsApp group. So okay dear students, see you in the next lecture. Till then, goodbye.